The human body is a marvel of nature. The heart is one of the main parts of the body which circulates blood continuously throughout our body to keep us alive. Arteries are blood vessels that carry oxygenated blood away from the heart, and veins are blood vessels through which blood returns to heart. The veins in the lower chambers of the heart are equipped with one-way valves that open when blood flows towards the heart and close if blood tends to drain downwards. Purified blood is returned to the arteries by the pumping action of the heart. The pressure exerted by circulating blood on the walls of blood vessels is due to this pumping action of the heart. The pressure of blood helps in two ways. First, it supplies blood to the brain. That is, it forces some of the circulating blood upwards against gravity into the carotid arteries, the two major arteries of the neck and head. Second, it forces the blood through the tiny capillaries in the tissues. The blood vessels are so narrow that the speed with which blood flows through them is negligible unless considerable arterial pressure exists. Blood pressure, BP, is the pressure due to the force exerted by circulating blood on the walls of blood vessels. The pressure in the lower and upper parts of the body are different when a person is in standing position. Whereas, the pressure is almost equal in different parts of the body when a person is lying down on a horizontal surface. The figure given shows the average pressures observed in the arteries in various parts of the human body, namely the brain, B, heart, H, and foot, F, while standing and lying down, where these pressures shown are averaged over a heart cycle. To find the pressure values, we use Bernoulli's equation, represented by P plus half rho V square plus rho GH equal to constant. The velocity of blood in the arteries at the three places in the human body is small, approximately 0.1 meters per second, which is negligible, and hence the kinetic energy term half rho V square can be neglected in the expression for Bernoulli's equation. Let the gauge pressures in the brain, heart, and foot be represented as PB, PH, and PF respectively. The typical values of height of the heart and the brain from the ground are HH is equal to 1.3 meters and HB is equal to 1.7 meters. As the reference is taken from the ground, the height of the foot, HF, is 0. The gauge pressures are related as PF is equal to PH plus rho GHH, which is equal to PB plus rho GHB, where rho represents the density of human blood, which is nearly 1060 kilograms per cubic meter. Substituting the values of heights from the ground and the density of blood, given that pH is equal to 13.3 kilopascal, we get pressure at the foot, PF, is equal to 26.8 kilopascals and PB is equal to 9.3 kilopascal. Hence, we observe variations in pressure in the lower and upper parts of the body, when a person is standing. As the vertical height of different parts of the body is almost the same when a person lies on a horizontal surface, the blood pressure is almost the same throughout the body when the person is lying down. Blood pressure is commonly measured in torricelli or millimeters of mercury. 1 millimeter of mercury is equal to 1 torricelli, which is equal to 0.133 kilopascal. The average pressure at the heart, pH, which is equal to 13.3 kilopascal, is equal to 100 millimeters of mercury. Pulse rates are measured by placing a finger over the wrist, where each pulse takes less than 1 second. During each pulse, the pressure in the heart and the circulatory system goes through a maximum as the blood is pumped by the heart and minimum as the heart relaxes. Thus, blood pressure is recorded as two numbers: the systolic pressure as the heart beats and the diastolic pressure as the heart relaxes between beats. Blood pressure is greatest when the heart contracts and lowest when it relaxes. Blood pressure is expressed in terms of the systolic pressure and diastolic pressure, which are 120 and 80 for a healthy body. Blood pressure is measured using an instrument called a sphygmomanometer in millimeters of mercury. The sphygmomanometer is designed to monitor blood pressure by measuring the force of the blood in the heart where the pressure is greatest. A sphygmomanometer consists of a hand bulb pump, a unit that displays the blood pressure reading, and an inflatable cuff that is usually wrapped around a person's upper arm and a stethoscope to listen to the sound. Blood pressure is usually measured at a person's upper arm for two reasons. The first one is that it is at the same level as the heart, and hence the measurements at this place provides values which are close to that at the heart. The second one is that the upper arm contains a single bone, which makes it easy to compress the brachial artery. The sphygmomanometer works on the principle that blood flows in the brachial or the upper arm artery can be made to go from laminar to turbulent by suitable compression. Turbulent flow is dissipative, and with the help of a stethoscope, the sound can be picked up. A sphygmomanometer cuff is wrapped around the subject's upper arm, just above the elbow, and a stethoscope is placed on the hollow of the elbow, over the brachial artery as shown in the figure. At first, the cuff is pumped up to a pressure of 180 millimeters of mercury, compressing the brachial artery, hence causing the artery to collapse once the systolic pressure is crossed. The blood flow through the brachial artery increases steadily until the pressure of the sphygmomanometer cuff falls below the diastolic pressure, approximately 80 millimeters of mercury. This is the point where the blood flow through the artery is laminar. The pressure in the cuff is then slowly reduced while a stethoscope placed just below the sac is used to listen to noises arising in the brachial artery. Here, the brachial artery opens up, causing volatile blood flow as the systolic pressure is reached. During this brief period, the blood velocity in the highly constricted artery is high and turbulent, and hence noisy. These noises are called Korotkov sounds and can be heard through a stethoscope as the pressure of the sphygmomanometer cuff falls below the diastolic pressure. When the pressure in the cuff is lowered further, the artery remains open for a longer portion of the heart cycle, but closed during the diastolic phase of the heartbeat, where the tapping sound is longer. When the pressure in the cuff reaches the diastolic pressure, the artery is open during the entire heart cycle, where we hear a steady continuous roar on the stethoscope. The blood pressure of a patient is represented as the ratio of systolic to diastolic pressure. For a healthy adult, it is 120 by 80 millimeters of mercury. If the pressure is above 140 by 90 millimeters of mercury, the person requires medical attention and advice, as high blood pressure will seriously damage the heart, kidney, and other organs and should be controlled. The blood flows in the artery, and the cause for a heart attack can be explained by using Bernoulli's principle. As the blood flow is constricted due to the accumulation of plaque on its interior walls, the heart needs a great force to drive the blood. While the blood rushes through the artery with high velocity, the internal pressure drops and the artery is collapsed due to external pressure. The heart exerts further pressure to open this artery and forces the blood through. The internal pressure once again drops due to the same reasons as the blood rushes through the opening, leading to a repeat collapse. This results in a heart attack.
A buoyant force or upthrust acts on a body immersed in a fluid at rest. When a body is immersed in a fluid in motion, it experiences a similar lift due to its motion. The lift experienced by the body by virtue of its motion is called dynamic lift. Aerodynamic lift is the dynamic lift experienced by a body when it is in motion in the air. In many games such as cricket or football, we notice that a spinning ball deviates from its parabolic trajectory as it moves through the air. This deviation can be partly explained on the basis of Bernoulli's principle. Consider a football in motion in the field and observe it from the close corners. Assume that the ball is not spinning as it moves through air, and consider its motion in a horizontal direction. This is equivalent to the situation where the air surrounding the ball has a laminar flow, and its flow can be visualized with streamlines around the ball as shown. The concentration of the streamlines represents the magnitude of the velocity of air. We observe that the streamlines are symmetric about the ball. From the symmetry of streamlines, it is clear that the velocity of the fluid, which in this case is air, above and below the ball at corresponding points is the same. This results in zero pressure difference at the points above and below the ball. The air, therefore, exerts no net vertical force on the ball. Now assume that the ball has a spinning motion about a horizontal axis in addition to its horizontal motion in the air. Let v be the velocity of air. While the ball spins, it drags the surrounding air along with it. If the surface of the ball is rough, then the amount of air dragged is greater. Let the net velocity of the air at the top of the ball be v1. The streamlines are crowded at the top of the ball and rarefied at the bottom of the ball, and are thus asymmetric about the ball. According to Bernoulli's principle, the sum of the pressure energy, gravitational energy, and kinetic energy per unit volume of the fluid at any point in it is constant. Thus, we have P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2, where P1 and P2 are the air pressures at the top and bottom of the ball and rho is the density of air. In this case, as the dimensions of the ball compared to the height of the ball from a reference level, say ground level, is much less, we neglect the difference in the height of the 2 points, above and below the ball, and thus H1 is equal to H2. Thus we have P1 plus half rho V1 square is equal to P2 plus half rho V2 square. As the velocity V1 is greater than velocity V2, we have pressure P1 less than pressure P2. Thus, the difference in the velocities of air results in the pressure difference between the lower and upper faces of the ball. This results in a net upward force on the ball. This dynamic lift, due to the additional spin motion of the ball along with its translational motion, is also referred to as the Magnus effect. The aerodynamic lift of an aeroplane can be explained by a similar principle. Let's consider an aerofoil to explain it. An aerofoil is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through the air. The cross-section of the wings of an aeroplane looks similar to that of the aerofoil shown with streamlines around it. When the aerofoil moves against the wind, the orientation of the foil relative to the flow direction causes the streamlines to crowd together near the foil. If the plane of the foil is tilted down to the horizontal, the streamlines are concentrated at the bottom. This shows that the velocity of air at the bottom of the foil is greater than at its top. If the plane of the foil is horizontal, the streamlines concentrate at its top due to its structure. If the plane of the foil is tilted above the horizontal as shown, the streamlines are concentrated at the top of the foil, indicating that the velocity of air at the top of the foil is greater than at its bottom. For an aeroplane, the dynamic lift can be found by the product of pressure difference and the area of the wings of the plane. As discussed for the aerofoil, the orientation of the aeroplane wing should be positioned such that its plane makes a small positive angle to the direction of air flow. If the angle of the plane of the wing is large, the plane stalls due to air resistance and air turbulence at the end of the wing. The fluids we encounter in our daily lives are not ideal ones and offer some resistance to motion. This resistance to fluid motion, or the internal friction that retards the flow of the fluid, is called viscosity. It can be compared to friction when a solid moves across a surface. This force, called viscous force, exists when there is relative motion between layers of the fluid. Suppose we consider a fluid such as oil in the form of a thin layer enclosed between two glass plates as shown. The bottom plate is fixed while the top plate is moved with a constant velocity v, relative to the fixed plate by applying a certain force. If the liquid between the plates is honey instead of oil, then a greater force is required to move the plate on the top with the same velocity. Thus, we conclude that honey is more viscous than oil. Consider the liquid between the two horizontal glass plates to be consisting of different layers. The liquid layer in contact with the surface has the same velocity as that of the surface. Thus, the layer in contact with the top surface moves with the velocity v. Similarly, the layer of the liquid in contact with the fixed surface at the bottom is at rest. The velocities of different intermediate layers that lie between the two plates increases uniformly from 0 at the bottom to v at the top. For any layer of liquid, its upper layer pulls it forward while the lower layer pulls it backward. This results in a force between the layers. This type of flow is known as laminar. Thus, different layers of the liquid slide over one another as shown. Now consider a liquid flowing through a hollow pipe instead of between two horizontal plates as discussed earlier. The liquid in the tube can be considered as different hollow cylindrical coaxial layers, with the axis passing through the center of the cylindrical tube. In this case, the velocity of the cylindrical layer in contact with the inner wall of the tube is 0, as the tube walls are stationary and the velocity keeps increasing towards the center. Thus, the velocity of the central cylindrical layer of the tube has the maximum value. Therefore, the velocity on a cylindrical surface in a tube is constant. Due to the relative motion between different layers of the liquid, a portion of the liquid which at some instant has the shape ABCD in its side view, takes the shape of AEFD after short interval of time delta t. During this time interval, the portion of the liquid considered has undergone a shear strain of delta x by L, where L is the distance between the topmost and bottommost layers of the portion of the liquid considered, and delta x is the lateral displacement of the top layer of the portion of the liquid. This is due to the shear stress on the portion of the liquid F by A. As fluids cannot resist shear stress, unlike solids, the strain in a flowing fluid increases with time continuously. Thus, it is not possible to measure the shear stress in the case of liquids as in solids. In fluids, it is found experimentally that stress depends on the rate of change of strain or the strain rate, which is denoted by the ratio of shear strain delta X by L to time delta T. Unlike a solid, here the stress is found experimentally to depend on the rate of change of strain or the strain rate. Thus, we have F by A proportional to delta X by L delta T. Therefore, the ratio of shear stress to strain rate is constant. This constant is called the coefficient of viscosity and is denoted by the Greek letter eta. It is also referred to as viscosity or dynamic viscosity in general. As delta X by delta T is the velocity v of the liquid layers, we can substitute v for the term in the expression, and then on simplifying, we get eta is equal to F by A into L by V. The SI unit of viscosity can be derived from the expression as shown. These are Newton second per meter square or Pascal second. In a similar manner, we can also derive the CGS unit of viscosity, which is dyne second per centimeter square. Substituting the CGS unit of dyne and on simplification, we get the CGS unit of viscosity as gram per centimeter per second. This CGS unit is also called poise, named after the scientist Jean-Louis Marie Poiseuille, and is denoted by the letter P. We define the SI unit of viscosity as follows. If a fluid with a viscosity of 1 Pascal second is placed between two plates, and one plate is pushed sideways with a shear stress of 1 Pascal, it moves a distance equal to the thickness of the layer between the plates in 1 second. We obtain the relationship between the SI and CGS unit of viscosity as follows. Thus, 1 Pascal second is equivalent to 10 poise. By definition, coefficient of viscosity can be expressed in terms of other physical quantities as shown. Thus, the dimensional formula of coefficient of viscosity can be derived from the dimensional formulae of the quantities in the expression as shown. Hence, the dimensional formula for coefficient of viscosity is ml power minus 1 and T power minus 1. Generally, thin liquids like water, alcohol, etc. are less viscous than thick liquids like coal tar, blood, glycerine, etc. Observe ghee in a container when it is warm. It is a common experience that ghee becomes more viscous while its temperature decreases and cools. We can reduce the viscosity of ghee in the container by heating it. Thus, we can conclude that the viscosity of liquids decreases with an increase in temperature. As the temperature of a liquid increases, the average speed of the molecules in the liquid increases, and the amount of time they spend in contact with their nearest neighbors decreases. Thus, as temperature increases, the average intermolecular force decreases, resulting in a decrease in viscosity. The coefficients of viscosity for some common fluids are listed in the table shown. The viscosity of blood and the sedimentation rate of blood cells are used to diagnose certain diseases. Similarly, the selection of lubricating oil used to reduce friction between various machine parts depends on the viscosity of the oil. From the table, it is obvious that the viscosity of gases increases with temperature. The viscosity of a gas increases as temperature increases due to the increase in the frequency of intermolecular collisions of the gas molecules at higher temperatures. Since the molecules in a gas usually fly freely through the available free space, anything that increases the number of times a molecule is in contact with another will decrease the ability of the molecules as a whole to engage in coordinated movement. The more these molecules collide with each other, the more disorganized their motion becomes. Thus, the restriction to the free flow of the gas increases, and hence its viscosity increases. Viscosity is normally independent of pressure. Since liquids are normally incompressible, an increase in pressure does not really bring the molecules significantly closer together. Thus, the increase in pressure of a liquid does not increase the intermolecular forces, and hence does not affect its viscosity. If an object heavier than a liquid is dropped in a liquid, it sinks. How quick it sinks depends mainly on the viscosity of the liquid. Consider a spherical solid object dropped into a long, vertical tube containing a viscous liquid. As the solid moves through the liquid in contact with the solid is dragged with it, establishing relative velocities between the layers of the liquid near the sphere so that viscous forces begin to act. The liquid exerts a viscous force on the solid to oppose its motion in the liquid. The magnitude of the viscous force on the solid depends on the shape, size, speed of motion of the solid, and the coefficient of viscosity of the liquid. If r is the radius of the spherical object, v is the velocity of the sphere in the liquid, and eta is the coefficient of viscosity, then the viscous force F on the sphere depends on r, v, and eta. Assuming that the force is proportional to the different powers, say A, B, and C of these quantities, we can obtain the dependence of the viscous force on these quantities using a dimensional analysis. Taking a proportionality constant K, we get viscous force F is equal to K into R power A into V power B into eta power C. The dimensional formula of F is mLT power minus 2. The dimensional formula of R, V, and eta are L, LT power minus 1 and mL power minus 1 and T power minus 1 respectively. Thus, taking the dimensions on both sides of the expression, we get mLT power minus 2 is equal to K into L power A into LT power minus 1 power B into ML power minus 1 T power minus 1 whole power C. As the constant K is dimensionless, we simplify the terms on both sides and equate the dimensions of the quantities M, L and T on either side of the equation to arrive at the values of the powers A, B and C. On simplifying the expressions, we get the values of A, B and C, each equal to 1. Thus, the equation for the viscous force F is obtained as equal to K eta R V. The value of the constant K is experimentally found to be 6 pi, and hence the viscous force is denoted by F is equal to 6 pi eta RV. This equation is known as Stokes' law, named after the person who derived it. Stokes' law states that at low velocities, the frictional force on a spherical body moving through a fluid at a constant velocity is equal to 6 pi times the product of the velocity, the fluid viscosity and the radius of the sphere. The various forces acting on the sphere, which is dropped into the liquid, are: the weight of the body, W is equal to mg acting downward, viscous force, F, acting upward, and the upthrust or the buoyant force B is equal to V rho g, also acting upward. Here, V is the volume of the sphere and rho is the density of the liquid. The weight of the sphere, W, and the buoyant force B are constant. However, the viscous force F acting upward against the motion of the sphere depends on the velocity. Initially, when the sphere is just dropped, the velocity of the sphere and hence the viscous force on it is 0. The force on the sphere at this instant is the result of the weight of the sphere, W, and the buoyant force B. As the weight W is greater than the buoyant force B, the resultant force at this instant acts downwards. Due to this downward force, the sphere accelerates, and thus the velocity of the sphere increases downwards. As the velocity increases, the viscous force F, which is equal to 6 pi eta RV, acting in the vertically upward direction, increases accordingly. Thus, the net force now is equal to W minus B minus F, which is equal to mg minus V rho g minus 6 pi eta RV. At a certain instant, the upward viscous force becomes equal to the force in the downward direction, and then the net force on the sphere is 0. Thus, the sphere attains a constant velocity, Vt, with which it reaches its terminal point, that is, the bottom of the tube. Hence, this velocity of the sphere is called the terminal velocity of the sphere. As the mass of the sphere can be expressed as V into rho s, where V is the volume of the sphere and rho s is the density of the material of the sphere. We can write 6 pi eta RVT is equal to V into rho s minus rho into g. Thus, the terminal velocity of the sphere is expressed as V into rho s minus rho into g by 6 pi eta r. Substituting the expression for the volume of the sphere 4 by 3 pi r cube and simplifying, we get the Vt as 2 by 9 r square into rho s minus rho into g by eta. As discussed earlier, for liquids of relatively low viscosity, their flow in a tube is laminar when the velocity is below a certain value called critical velocity. If the speed of the liquid crosses the critical velocity, it becomes turbulent. The nature of the flow of the liquid, that is, whether it is laminar or turbulent, mainly depends on the density, rho, velocity, v, coefficient of viscosity of the liquid, eta, and also the dimension of the tube, namely its diameter, d. Osborne Reynolds, who was a prominent innovator in the understanding of fluid dynamics, observed that turbulent flow is less likely for viscous fluid flowing at low rates. He defined a dimensionless number, whose value gives an approximate idea whether the flow would be turbulent. This number is called Reynolds number, Re, given by rho Vd by eta, where rho is the density of the liquid, v is the velocity of the liquid, d is the diameter of the tube, and eta is the coefficient of viscosity of the liquid. Reynolds number plays a key role in determining the nature of flow of a given fluid. It is found that for the flow of a liquid in a tube, if the number is less than 2300, the flow of the fluid is steady. If the number is between 2300 and 4000, then laminar and turbulent flows are possible, where there is a transition of the flow from laminar to turbulence. If the number is greater than 4000, the flow is completely turbulent.